As you may have heard, my name is Victor Parque from Waseda University in Tokyo, Japan. So I will talk about Steiner trees and the work we have been doing on the plane, especially a path planning on the planar maps with obstacles. So basically, we're inspired in the following problem or the following question: what is the network of minimum length connecting endpoints in the Euclidean plane? And as you may see in the left side, you are seeing probably two wires. And the object of computing this kind of bundle is to ensure a minimal length connectivity of joined wires. This problem usually happens in the wireless harness problem in cars or so. For example, there are other applications in which, for example, you may have a robot, for example, in the planar environment, and the red point directs kind of a central robot trying to coordinate some actions or trying to control the nodes in the leaves. And the object of this research is to compute the topology of the tree. And of course, this problem is related to the Steiner tree problem. We can assume that the root is fixed or non-fixed as in this case here. In the below case, you are going to see that you are given endpoints arbitrarily on the plane, and the object is to compute the topology of the tree that tries to minimize the network connectivity. So basically, this problem appears in the important applications, for example, in the physical or the design of physical neural networks, and also you are going to see this problem in the design of communication and distribution networks. For example, the Steiner swarms is a very recent hot research topic in the robotics community. And also you're going to see this problem appearing in the circuit design, for example, in the VLSI field, in which the problem is to design optimal circuits connecting many components in the chip. You're going to see also this problem or this instance problem in the graph visualization problem. For example, when you're given lots of nodes in a map and you want to see a compact visualization of the network. And this problem is also related to some folding problems. For example, if you're asking yourself, what is the unfolding or configuration with a minimal perimeter of this cube? Well, actually, you're going to see a kind of Steiner tree defining the cut of the unfolding of this cube. And also, Steiner trees appears in some natural problems. For example, if you're given a kind of a planar table in which you're having 3 holes, for example, and you're giving 3 equal masses, and you're going to find that the kind of Steiner tree appears in the configuration or the physical configuration of this physical phenomena. You're going to see also Steiner trees in the films when they are folded with bubbles. For example, you are going to see for 4 points and then a film which is covering the subbubbles, you're going to see a kind of a Steiner tree forming naturally in this phenomena. In practical applications or research applications, we are going to see Steiner trees or the minimal trees, especially in recent conferences. For example, DESPS trying to design some microfluid biochips. Here, they assume that, for example, the tree is orthogonal. In this case, we are trying to extend this approach in order to assume that the trees can not be restricted to the orthogonal case. Also, this problem appears, as I already said before, in the Steiner swarms, when a robot tries to control or tries to build a distributed control network over some kind of unknown environment. Also, this problem appears in a wire harness problem when we're trying to design a kind of a wiring connectivity in the vehicle systems. And there are lots of papers and lots of engineering applications related to this problem. Basically, the Steiner trees arise in the kind of 1659 when, or 1659, when Pierre de Fermat formulated the following question. You are given 3 points, then try to find the internal point that tries to minimize the length of the tree. And then there was a person, there was Evangelista Torricelli, he was Italian mathematician. He solved the problem, but it was a student, Vincenzo Viviani, the one who published the results. Basically, the solution is based on the geometrical configuration of 2 triangles, especially these triangles are kind of equilateral triangles. And by crossing these kind of lines, you're actually trying to find the optimal point that defines the Fermat point. And then from this Fermat point, you are given a kind of optimal tree. This problem has been studied also in in the 6th or the 1810s. For example, it was Joseph Gergon, the first one who studied the problem in considering more than 3 cases. He studied the cases, for example, for three nodes in which the angle may be more than 120 degrees, or he studied other more complicated cases such as the ones you see here. This problem has also attracted the attention of Gauss. He was trying to design a kind of railroad network in Germany, trying to connect 4 cities there. And he tried to send a letter to Schumacher in this year, trying to outline the possible configuration of the optimal tree. And this problem was quite famous because many people believe that Gauss was trying to help his son to build a kind of a military network in Germany. And then this problem also attracted the attention of many researchers along the past decades. To my best of knowledge, I think the best a kind of literature review or a kind of a summary of all the best works in the Steiner trees with obstacles are given as the following. It was McGregor and Liebman in the 1979 trying to study the Steiner trees with 3 nodes with 1 convex obstacle. For example, you can see many different convex obstacles here and 3 nodes and trying to obtain the optimal tree in such kind of configurations. And it is more or less about 20 years ago, the case in which we can have non-convex obstacles. And it is about also Zachariasen was one of the first ones trying to provide the configuration of more complicated networks or complicated configurations of Steiner trees, but considering basically complex obstacles on the plane. There is also much more recent work using kind of genetic algorithms. It was published in the ASME Journal of Mechanical Design. There, the authors assume that the problem is to find these kind of intermediate points, given these blue points, and then the problem then translates into a kind of optimization problem, trying to minimize the total length of the tree. So here the user has to design or has to guess where the possible configuration or the possible topology of the tree can be. And based on that guess, we can encode the intermediate point in the Euclidean domain. And from there, the authors designed a kind of multi-objective algorithm based on GA, in which they consider the length of the tree and the cost of building such kind of tree. This is kind of a state-of-the-art in the design of Steiner trees using kind of a non-convex optimization approach. And then here we try to extend such kind of works in order to consider the following points. The first point that we consider is the network topology. We assume that we don't know or we don't know a priori what could be the network topology of the Steiner tree. The second consideration is that we consider any kind of obstacles on the plane, could be convex or non-convex. And then the third consideration is that we try to be as much efficiently as possible and try to be as much scalable as possible in the problem domain. So for example, if we are given this kind of planar configuration of the obstacles and then nodes are arbitrarily configured over the Euclidean domain, the possible output or solution that our algorithm tries to find is what could be the optimal tree connecting these nodes, and what kind of intermediate points could be there, and what could be the topology of such kind of tree. Then our approach is based on the following ideas. Basically, this kind of approach combines lots of algorithms. So that's why we call our paper a kind of a hybrid heuristics. We try to explain here the most important ideas. So I would appreciate if you could go to the paper to get into more into the details of these ideas. The first, we assume that we are giving a map, and then we assume that the nodes are just arbitrarily given over the 2D Euclidean domain. And then from there, we kind of guess or assume that the root is given in a certain configuration of the map. From there, we can actually get a shortest path to every node or to every end node in the Euclidean domain. From the shortest paths, let's say A, B, C, D, and E, F, we can compute a kind of hierarchical clustering of the short spots. This kind of hierarchical clustering or dendrogram is actually going to be a kind of guide in order to find the intermediate points, trying to optimize an optimal tree or trying to get the optimal tree. For example, if you are given in a situation in which we are having root A and root B, then we must find a kind of intermediate point there, trying to minimize a kind of in a kind of a local search situation here. So in other words, we try to do lots of local search optimizations guided by this dendrogram. And this kind of dendrogram is a kind of guidance mechanism to the more global optimization approach. So in such a way, we are trying to build the tree in the two ways. First, we go from the bottom to the top. Then after that, we finish from the top. We go in the opposite direction from the top to the bottom. So we try to replicate this kind of two approaches, and then after that, of course, we can also use non-convex optimization approaches in order to optimize the location of the root, and then for any kind of root, we can obtain any kind of topology guided by this dendrogram. The other basic idea is how to bundle the roots. In the previous slide, I explained here that it is important to actually compute the intermediate nodes. For example, how to compute such kind of nodes is basically guided by the following approach. For example, if you are given possible roots, such as group 1 here, or module 1, or group 2 here, then there is a possible way in which we can have such kind of root bundling. Basically, we try to compute two intermediate points such that we try to minimize the total length of the tree over the modules. So if we have a minimization in this domain, we can obtain a tree in this module, and we can obtain another tree in this module as well. Given these two modules, well, actually we can compute another tree. We can compute another tree in the hierarchical approach guided by the dendrogram, which was explained before. So in this approach, in the bundling approach, we try to find the bifurcation points or intermediate points using a kind of local search. So here in our approach, we are using a NelderMet or the fmin search from MATLAB. And the fitness is completely tree length. So this is just a completely local search over hierarchical domain. We also use the following nature-inspired tree operations. Basically, we assume that the output of the dendrogram of the hierarchical clustering that is given here, it's going to be a kind of binary tree. So we're going to find the necessity of joining trees or cutting the leaves whenever the fitness is desired to be improved or not. So if we do so, we consider the following operators. For example, we can consider the operation to expand. For example, given leaves U and B, we can obtain a kind of intermediate root X, which was explained before. We can also shrink some kind of the nodes. For example, if we want to delete this intermediate node, then the potential subtrees are going to be becoming like something like this. So there is also a merging operator when, for example, this module is going to join to this module, then we are going to delete all the parent of these nodes, and these nodes are going to be becoming children of these nodes, such as shown here. So this is actually resembling a kind of a mutation or especially mutation operations on the topological space or the structure of the tree. And then another very important point is how to represent the points in the map in order to compute intermediate points. There are many possible representations, especially to represent points in the Euclidean domain. There is a grid-based representation, or there is also that kind of geometrical representation. However, the grid representation is actually inaccurate for large-scale applications, and also it consumes lots of memory when the map becomes very large. And the geometrical approach is somehow complicated whenever we are trying to deal with triangulations, especially in the path planning configuration environments. So the important questions here is it possible to devise some kind of representation that actually is not depending on the configuration or the encoding of the planar space, and also is it possible to define some kind of encoding such as this is scalable, so that it doesn't depend actually on the geometry or the number of cells in the map. We use actually the following representation. We triangulate the map. Based on the triangles, we enumerate every triangle from 1 to some given integer. And from those triangles, we define internal points inside the triangle. So in other words, we are trying to build some kind of a mapping from the some kind of mapping from the non-convex space, because these obstacles represent some kind of holes, and that represents a non-convex space. So some kind of mapping from the non-convex space to the convex space. So in such way, any point in the map is given by the three tuple. This I represents a triangle or the order of the triangle in the map. For example, it could be 1, 2, 3, or 13, or 4, or 23. And these alpha and beta are real constants between 0 and 1. And this alpha beta represents actually some kind of a normalized coordinates, which allows you to represent any point inside the triangle. In such way, once we are given this three tuple, we can easily convert the three tuple in the Euclidean domain. If we can convert in the Euclidean domain, we can actually obtain the Cartesian coordinate given this I, alpha, and beta by this relationship here. So in such way, we actually have one good advantage. Any point in the map is in a free space. That means we don't need to check if the point is inside a hole or outside a hole, because any point encoded by this three tuple is actually outside a hole. And in such way, we can sample any point or any intermediate point for Steiner trees in a very efficient way. Our approach, in summary, we use some kind of shortest paths. We triangulate the map, and we devise a very nice encoding. And then based on that, we try to build a trees in a hierarchical way by using some lots of local search optimizations and guided by some kind of mutation operators on the topological space. And of course, we can obtain optimal trees in that sense. We have devised we can show some examples. For example, here we assume that the root is fixed, and the end nodes are given by the blue nodes here. These kind of arbitrary obstacles are consisting of non-convex shapes, and the output or that our approach is trying to assume or compute is this kind of topology. For this kind of environment, the root is given in the red node here. And here we are assuming that all the obstacles are kind of rectangles with horizontal or vertical configurations. Here, this is the topology. And for this case, we are considering this kind of a square like obstacles in the plane. And here, for this case, this is a kind of example for the minimal Steiner tree. Well, we have actually done lots of experiments. We can say that from the experimental point of view, we can get lots of minimal trees, but there are lots of works to do in terms of theoretical, especially theoretical analysis, and lots of proofs in terms of convergence. And then we actually try to find also how scalable is our approach. In the three types of maps that we have been studying, for example, map 1, map 2, map 3, here we, in the x-axis, we denote the number of edges or the edges of the tree. And here we devise how much time the computer takes in order to build the Steiner tree. So here we try from 5 to 20, and we can see something resembling a linear approach, but we have to be very kind of take these results with a grain of sand, because we have to take with lots of edges here, for example, 100 or 1,000 or so. But for very small cases, which are the interest in our approach, we are interested in just not so large cases, because we are interested in the robotics applications. For these cases, we can say that we can take the Steiner trees between 5 seconds or 10 seconds here, for 20 edges, we can take for about 12 seconds, and it doesn't change, and the time doesn't change so much if we consider the different topologies of the map. So for a small scale, we can say that we can get some kind of attractive scalability in the linear sense. We also did some experiments in order to verify or evaluate if our approach is able to obtain minimal trees in the sense of obtaining the topology of the tree for arbitrary nodes which are distributed on the Euclidean domain. So here we consider 3 maps, as you have already seen. We consider five types of different algorithms. These most of them are basically differential evolution, and here we have one types of PSO with this is a kind of niching property. We can also have the direct, which is based on the branch and bound. This differential evolution is basically combining global and local interpolation vectors, and this one is based on the ratio. This one is based on the a successful parent selection. Most of them are trying to find the optimal routes in terms of different ways of balancing exploration and exploitation. So we wanted to know what could be the effect of such kind of different strategies on obtaining the quality in obtaining the quality of the trees. For all the experiments, we assume that we have 20 nodes in the map, and for each kind of map, we assume that we have 10 different instances of node configuration in the map, and also we run 20 independent runs per each instance. Some examples, for example, you are going to see that for arbitrary configuration here, our optimal tree is something like that, and the typical convergence is something like that. We can see that we can take for about 200 fitness evaluations in order to get more or less a kind of minimal tree. For this example, you are going to see that we can also say we can get somehow a kind of minimal trees in 200 fitness evaluations. And then for this case, we can also have this kind of topology here, which we can say that for about, we can spend 200 functional evaluations in order to get some kind of minimal tree. In terms of mean convergence and statistical analysis, we can see the following results. Basically, the branch and bound is quite successful in the maps of the type 1. That means in the maps which are non-convex, but it's not so successful in the map of types 2, which is this kind of symmetric configurations of the map over independent runs, as shown by the p-values here. However, in the map number 3, for example, these maps, the direct search is also somehow competitive. One of the reasons we can argue is that basically the direct is trying to divide the search space and then try to find the intermediate points as much as possible. And direct is going to have lots of beneficial results when the number of triangles are not so much, especially when the map becomes complicated. Well, the triangulation is actually the size of the triangles are not going to be so large, but in this case, the size of the triangles actually are going to be very large, and that is a kind of somehow of some type of intuition in order to argue whether direct could be better than other evolutionary computing schemes in trying to find the optimal routes. We also try to get some experiments in some real or some environments which are reminiscent of real world environments. For example, we try map number 1 here and map number 2 here under different types of configurations. And here we can see that in about 1,000 evaluations, we can get some kind of a nice tree over this kind of a difficult environment. And for this case, well, this is a kind of a deployment of the tree. This is the root, and all the black nodes are the leaves, as you may see from different angles. In the second case, in about 500 evaluations, we can get some kind of minimal tree. The deployment of this map, the root is given by the blue node here, and the leaves are given by the green nodes, as you may see here. and you are going to see lots of different views of this tree, which is deployed on the map. Also, we consider the possibility of adding partitions. I was somehow inspired by the talk given yesterday by Verel. He was actually commenting on the possibility of considering partitions when studying the DESPS problem. So actually, this kind of idea can also be applied in our approach. If we consider partitions in the Steiner trees, we can actually compute these Steiner trees in a kind of modular way, and from there we can consider further for future work in order to consider some possible crossover or some possible joining of the trees and so on. So that is a kind of a future work we would like to take on our next agenda. This is also another view of the possible trees when we try to consider the partitions over the large scale domain. So considering the partitions is quite important when we deal with the very large number of nodes on the map, so that our computations can be somehow parallelized and can be quite efficient in that sense. In conclusion, we present our approach to compute minimal trees or Steiner trees as efficiently as possible. We consider any kind of arbitrary polygonal maps in the Euclidean domain. We argue that our approach is scalable. We want to work in the future applications concerning the network design problem or the wire harness problem and all other problems related to graph design or planning or graph planning in the robotics applications. Thank you very much. I would appreciate if you could have some comment or some feedback or questions. Thank you very much.
Thank you very much, Victor. So I think we have time for 1 or 2 questions maybe. So anyone? So just raise your hand or just take the liberty to talk directly, since we are not so many people. I think it's doable. Any question from the audience? Okay, so I'll have one. So actually one relates, since you mentioned about the talk from Verel yesterday. I was wondering in your experimental analysis whether this actually makes sense to compare the different algorithms in terms of the number of calls to the evaluation functions. Because my guess is that if you make some change, so if I understood correctly, you make some local changes by using local operators. And my guess is that given the operator you're using, you do not evaluate a solution from scratch every time. Like when you have a current solution and you apply a mutation operator, only small part of the solution actually changes. And do you still evaluate the whole solution from scratch, or you can do this somehow incrementally, just looking at the local changes?
Oh, yeah. Basically, when we are trying to evaluate the fitness of the tree, we are trying to evaluate only once the root has changed. So if the root changes, then all these parts are not going to change actually. For example, if the topology of the tree changes, naturally it will be the consequence of the dendrogram, which is shown by, let me see, this slide. This slide will tell a lot about how the topology of the tree is changing. And if the change is local, if the change is happening around here, then naturally it will not induce in a kind of a huge change over this space. So yeah, basically fitness evaluations only happen when the root has changed in location and whether the topology of the tree is changing.
Okay, so this is how you count. Actually, you count an evaluation as one once the root node changes position, right? In all the approaches. Okay.
Yes.